Okay, so I'm going to show you this, how I would do this problem from page 99 in chapter 6 about the normal approximation of the binomial distribution. So what they're telling me, I mean, in last week, what we did when we were looking at the binomial distribution, we would have done this. We said, okay, I've got a 13% success rate of everybody being left-handed, of people being left-handed. I've got n is 100 students, and I'm concerned with if I'll have enough pairs of left-handed scissors. So what I'm really interested in, I'm interested in the probability that I'll have more than 20 people show up. If I have more than 20 left-handed people show up. So what we did last week was well, we use that binomial calculator, and I just have a different version of that pulled up here. Let me come there. Let me go there and show you. Okay. So here's a different kind of binomial distribution calculator. I had it linked to, I don't know if you used it, but it's same kind of deal. It's just not, it doesn't give you quite as much information, but for our purposes, it's going to give us plenty. So I've got my n is 100. I'm interested in 20 or more people, and my probability of success is 0.13. So this calculator is saying it's a 0.0, less than a 5% chance. So is this unusual? Yeah, I mean, that's less than 5%. So that would be considered, it's not likely we're going to get more than 20 left-handed people show up. Okay, so now we're going to take a step further with this, and now we're going to see, well, normal distributions are really handy to use, and can we use a normal distribution here? Well, one of the things, can we approximate this distribution with a normal distribution is what we're trying to do. So one of the criteria is that n times p has to be bigger than, oh no, I don't remember what Dr. Stevens says. Is he a 5-person or is he a 10-person? Let's come up and take a look. Some textbooks say 10, some textbooks say not, it's 5. And since we're trying to make WebAssign happy, we'll better do what the book says. Let's see here. Okay, I'm going to stop this. While I'm looking, I'm going to pause this video and come back. Here it is. Dr. Stevens says right here, if n times p and n times 1 minus p are both greater than 5, then we have a normal distribution. So if we come back and look at that binomial distribution applet, here we go. Let's take a look and see if this n times p is bigger than 5. So I've got 0.13 times 100. Oh yeah, that's 13. So that's bigger than 5. Check. And then we're going to do 1 minus 0.13, which is 0.87, and 0.87 times 100 is also bigger than 5. So according to his rule, this is a normal distribution. I use this applet here because I want you to look at the graph of this binomial distribution. And I hope you see this looks pretty normal to me. I see it looks unimodal. There's one, well, there's in the middle here, but there's a peak in the middle, and then it tails off symmetrically to both sides. So this is a normal distribution, and it's a pretty close to normal distribution. So it looks like this is why he says 5. What if I think I've done this elsewhere, but in case I haven't, or you haven't watched that video, what if we shrink this sample size down to something so when I go 0.13 times 100, it doesn't look normal anymore. Let me clear off my writing so I can get that. How about, let's see, if I do 20, yeah, I think 20 will make it so it's not too much. So you see, if I only have a sample size of 20 and n equals, and probability of success is 13, that no longer looks normal. Using the normal approximation wouldn't be a good idea here because that's not a very normal distribution. So that's why they have that situation. I think, let's see, who's a calculator? I'm gonna do a little division. Let's see, I just want to see what's the minimum sample size that'll do that. So let's see, I could have 5 divided, whoops, turn it on. 5 divided by 0.13. So it looks like I have to have a sample size of about 39 before it passes that condition. And even then you can see it kind of doesn't really, it still get this kind of skew off to the right a little bit, but it's not bad. I mean, we crank it up to 50, I think it's fine. Yeah, see, it's better, still a little skew. Certainly at 100, that's the normal distribution. All right, so this red ink, that's red, so that's with the binomial distribution. Now we want to see, I'd like to see how close it compares. If we say, well, let's just, instead of doing this with a binomial distribution, let's see if we use a normal distribution if we're good. Because the nice thing about the normal distribution is then we start using some techniques we're going to learn in chapter 7 and 8, and that's why we want to do this. Those techniques don't work for the binomial distribution. So one thing for the normal distribution, since we know that passes that criteria that it looks like a normal distribution, when we talk about normal distributions, when we talk about any distributions, we want to talk about the shape. Well, this is normal. And then the mean, and we know from our work last week that the mean of this distribution is 100 times the probability of success, which is 13. Take a look at this applet, actually tells us that. And then the standard deviation for this distribution is 100 times 0.13, 13, Dan. Times 1 minus 13, which I think is 0.87. And then we're going to take the square root of that mess. And since this applet already did it for us, that's the standard deviation. So now to do this by hand, you do what Dr. Stevens did, find a z-score, look it up in the table, so on and so forth. Now, I'm going to write down the standard deviation right here so it carries along to the next screen with me. So I'm going to use a normal distribution, and I've been pointing you towards this David Lane applet, and I'm going to change my mean to 13. I'm going to change my standard deviation to 3.363. And then I want to know more than 20 scissors, more than 20 left-handed people show up. And see, it's a little bit smaller, probability. And I'm pretty sure that's what Dr. Stephen got, or something along those lines. Maybe it's not quite that much because he had to, the z-score table is not as exact. It's more limited with the values. I'm probably going, what is the z-score for this? I'm doing, let's see, I'll just do that. Well, what is the z-score for this? Turn my board back on. So I've got a z-score of, let's see, I'm interested in 20 minus 13 divided by 3.363. So that's 7 divided by 3.363, and 7 divided by 3.360. I'm sure you've watched other videos with this and done it yourself. So I'm getting a z-score 2.08, 1, blah, blah, blah. So the best the table can do is 0.08, so 2.08. So that's why it's probably going to be a little bit different than that number. Okay, so that's how you use the David Lane applet to do this problem. Find the mean, check, make sure it's going to be a normal distribution, and then go ahead and find the mean, standard deviation, use the applet. All right, hopefully this helps.